Okay, so welcome to the last lecture of this course here in this winter term. And what we discussed so far in the course were mainly the so-called backends or optimization engines or probabilistic estimation techniques that were running kind of in the background solving the SLAM problem. And today I would like to give a very, of course, brief, short overview about frontends and one important aspect inside successful frontends on how to determine if a constraint is likely to be a correct one. So we are still interested in avoiding to add wrong constraints, although we've learned that there are techniques which can deal with outliers in the data association. So if we have wrong constraints, there are techniques that are able to deal with that. But of course, we are still interested on adding as few false positives as possible. And so this is related to the front end. And so what my goal is for today, I will introduce three kind of small front end systems on a kind of very abstract level, just giving you the idea on how they work with different sensors. And then in the second part of this talk today, I would like to stress on what kind of conditions should such a constraint fulfill, or the matchings of the local environment fulfill in order to, let's say, I don't want to say ensure to be outlier free, but to reduce the probability that this is actually an outlier match. So we're talking about front ends today, and what we learned so far, we have our graph. So you've seen this picture a few times during the course here that move through the environment. We have our nodes and we have constraints between those nodes. And we have loop closings when the robot observes the same part of the environment. And so far, we always assume these constraints are given. So these errors here, we assume to be given. And today, we would like to look at the case, how do we actually generate those errors? So these errors here, these constraints, which are successive constraints, that should be kind of clear. That can be simply odometry information or the result of an incremental scan matcher. So it's something that you have seen already here in the course, that you know how that works. But the important ones are actually those loop closing constraints. So, or even if the robot revisits the same place, kind of constraints which you can, let's say, informally call localization constraints. When the robot moves in an existing part or in a part of the environment it has seen so far and adds new constraints between its current observations and the observations that the robot obtained in the past. So you also seen this figure already in the past. This is the two main components of the SLAM system, so our back end and the front end. So far, we mainly looked here into the graph optimization. So the raw data comes in, the graph is constructed, the constraints are generated, the graph is given to the back end optimizes the graph and returns the new node positions back to the front end, and then the front end uses this information together with the new sensor information to generate new constraints. So far we have been looking to this part, and today we would like to look into this second part over here. So that's the goal. So how do we get those constraints? We get those constraints typically by matching observations. So we have different observations depending on our platform. That can be whatever, stereo camera, that can be a laser rangefinder, or different types of sensor modalities. And for every sensor, of course, there's a different way of obtaining those constraints. And those constraints may take into account what the sensor actually sees, how kind of unique is the data that the sensor generates for a specific area, or let's say, look all corridors exactly the same if you only rely on laser range data and the corridors all look exactly the same from the laser range data point of view. Then we may take that differently into account as if we have a corridor where we have a lot of whatever unique markers glued to the walls, and we have a camera and can perfectly observe those markers. So depending on what we see, what assumptions we make about our observations, this task can be very hard or not that hard. And what typical approaches are is if we go for laser range data is dense scan matching. So we really take our raw laser range information and try to align those different laser scans that we obtained at different points in time. And if we can match them well, we may say, okay, this part of the environment I see at the moment looks very similar to the part of the environment that I've seen so far or in the past, and therefore it is quite likely that we are at the same place. Other approaches use features. For example, we had the Victoria Park, where trees have been extracted, in this case from the laser range data, so the trunks of trees. And every trunk of a tree was seen as one feature or one landmark. and the robot mapped those landmarks by checking for, let's say, fitting circles into the laser range data, and whenever it found a good circle, say that's likely to be a trunk of a tree, and it uses it as a landmark. The third class of approaches uses feature descriptors. Most popular ones are, for example, SIFT and SURF. These are two features which you can extract from image data and which kind of describe the local surrounding of the place where this descriptor is computed. And if you have a lot of those descriptors in an image, you have a typically quite good description of the image. So you can just match those descriptors, and based on those descriptors, identify if two images are recorded from the same place. Of course, this is not free of errors and free of flaws, but you can match surprisingly large databases of images using those descriptors. So these are three popular techniques or sensor information that front-ends use in order to make the data association, and we will actually look into those with very short small examples during this course today. Okay, so we're typically in the situation we say, okay, the robot is currently, let's say, at location A, and let's assume the blue circle over here is a sensor range of what the robot sees. And we know in our, let's say, graph or post graph that we have built so far, we have two other places, B1 and B2. So these are places where the robot has been in the past. And I can estimate where those locations B1 and B2 are relative to the current pose of the robot, which is here indicated with A. So I can say, okay, given I'm here at the moment, and that's my sensor range, I can compute where are those other poses. So in this case, B1 and B2. Just two examples, could be more, obviously. And then I can also estimate what is the uncertainty of those poses B1 and B2 relative to A. And I do that by eliminating the node A from my linear system and then inverting the resulting Hessian and looking to the main diagonal blocks. This gives me the uncertainty, here indicated by these dashed lines, where B1 is relative to A, and the same here, where is B2 relative to A. So based on this information, I know I can have an estimate of, given my current pose, where is B1, where is B2, together with the associated uncertainty estimates. Okay, what I then do, I kind of can extend the uncertainty ellipse by kind of the visibility area of my scanner and say, okay, say if the robot was standing over here, that's the area it may have observed. Then I can simply check, is the current sensor range, is there an overlap between the current sensor range and the possible observation that I obtained from B1 or B2? And if I found places for which this holds, and this is the case for B1, because let's say if the robot in reality was sitting here, let's say these are as a 2 sigma bound, then you can say with 95% probability B1 sits in this ellipse. And they say if it was sitting here, this was a sensor range, so there's an overlap in the sensor range. I may see the same feature descriptors or whatever I'm looking into, and I can argue that I may need to check if A and B are seeing the same part of the environment in order to look for loop closing constraints. In contrast to that, if I look to B2, I can say, okay, the uncertainty of B2 extended with the visibility range of my sensor by no means overlaps with A. So it's extremely unlikely that A can match B2. And typically, you ignore those cases. So if you say, whatever, you take the 2 or 3 sigma bound of your estimate, and then say everything which is outside the 3 sigma bound, I'm not looking for potential loop closures. And so in this case, in this example, you would check if what the robot sees right now in A matches with what the robot has seen here in B1. And if you find a match, you may accept that. But you don't even look into B2. So based on the current uncertainty of the robot and not the current uncertainty, the uncertainty estimate that the robot has at the moment about places where it has been in the past, it makes a decision, should I look for loop closing constraints or not. So in this case, the views may overlap, so I really need to inspect my sensor data and see if I find correspondences between what I have seen in B1 and what I've seen in A. But here, the fuse basically cannot overlap, or the probability is so extremely small that I kind of ignored that. Okay, any question about this idea so far? Because we will need that later on. Okay, that's good. Okay, how to obtain the uncertainty? So how do I compute this uncertainty here before? I said, okay, I can do that by estimating the uncertainty relative to the current pose of the robot, which was here indicated with A, which I can obtain by inverting the Hessian. The problem is with inverting the Hessian in practice, this is a pretty expensive operation. So you actually want to try to avoid inverting this large matrix. You can do an approximation, what actually most systems in practice do to do that more efficiently. And this is a thing where they say, okay, we simply ignore the loop closures for the moment, just for estimating the uncertainty here. And you just do what is also called a Dijkstra expansion. So we propagate the uncertainties through the graph. So where the robot is right now, I assume is 0 uncertainty. And then I say, okay, I'm traversing through the next edge, the edge which generates the smallest increase of uncertainty to the next node. And I go on and always increase the uncertainty until I reach all the poses I'm interested in looking into. What this does is ignores the loop closures. So the uncertainty estimates are too big. But you can still argue that, okay, the uncertainty estimates I get are too big, but I can compute this extremely efficient. And I may inspect a few places too much, but I should get all the places which I need to inspect in order to make sure I find loop closures with whatever, 95% probability. So this is what is done, just as a side note, what is done in practice to avoid inverting this matrix H. Because so far we really tried to explicitly invert it. We used whatever Sperse-Cholesky decomposition or whatever techniques we used to not invert it explicitly, and therefore one actually tries also to invert this matrix in the data association step. So it's just kind of a side note. And what we do then, we just check which areas overlap, and if there's an overlap in the area between the current scan of the sensor range of the robot here and the sensor range of the robot at that point, I say, okay, this may be a match. This may not be a match. Okay, next question is, how do I determine is there a match or not? So let's say we have assumed, okay, my current observation matches with the observation, whatever, the place I've seen 20 minutes ago. How do I proceed? And this strongly depends on the laser data, or on the data. And here's one example of a very simplistic front end, which will try to identify constraints, which uses iterative closest point, so a form of scan matching, and tries to find a match. So how could we do that? So for the first thing we do, we estimate the uncertainty of the other poses relative to the current pose of the robot. So that's what we discussed so far. Given we have that, we take those poses which are in the air, we may just sample poses in those areas. So just randomly draw poses. So if I go back to my example, we take A, okay, I select, okay, B is a good potential match. So just sample random locations here close to B. And what I then do from every of those sampled points, I apply scan matching, in this case the iterative closest point algorithm. So I try to align the current observation with the observation or with a local map that has been built in this place B. And then I just see, okay, how well do those observations align, or how well does my current observation align with the local map I've built so far? Let's looking into the sum of the squared distances between the corresponding endpoints, or those endpoints which I regarded as corresponding points. And if this is above a certain threshold, I accept the match. So, okay, that's it. Looks the same. Here I go. That's a constraint. That's a very simplistic technique. Of course, you can do much better, but this is kind of the basics of most laser-based front ends today. Of course, you may have different techniques. You don't take a stupid threshold. You may use things like ransack. You may even use better initializations. You may use better matching algorithms. You may build local maps and try to match local maps in order to take more information into account. But in the end, the core idea more or less boils down to that. Again, you can extend or improve all those aspects here, but that's kind of the basic decision based on laser range data. are two places, or given an initial guess, what's the transformation of the locations from which those two scans have been taken. Okay, where do you see problems here? Does this work perfectly, or where would you see the failure points for this approach? So if you're a customer and I propose you this solution, what would be maybe your argument against that? Would you buy that, this approach which I propose you? Good, should do that. Where do you see potential problems of this approach, given what you have seen so far?
So if you just build local maps and they are somehow symmetrical, so you can match these different styles.
Absolutely correct. So if we have, let's say, a symmetric or partially symmetric scenes, say a corridor, which I can match this way or that way. It's one example where this approach would say, oh, perfect match, great, I got it. Looks perfectly. Every single endpoint matches perfectly. I'm done. Maybe not. That's one point, which may be a problem. And so if you it's an absolutely correct observation, this can happen. Where would you identify this problem in this list of approaches? So where's the problem over there?
In the initialization?
Yeah, so it's a combination of the iterative closest point algorithm and the initialization. So ICP depends on the initial guess, and it just finds one solution. And it may be the right solution, but as you pointed out in your example, it may be the wrong solution. So ICP is sensitive to the initial guess, and as a result of that, we may end up in a local minima. So in something which looks like a match, but in reality is not a match. Other things we may identify is how do I sample possible locations where the platform can be? If this is the uncertainty is a very large area, I may need to sample a lot of different poses in order to do that efficiently. So how do I find actually a good initial guess? And so these are typical problems that those approaches have. So ICP is sensitive to the initial guess. We have local minima. We may have an inefficient sampling strategy. So how do I generate possible initial guesses for my ICP iterations? Just accepting something based on a threshold is always something which someone might dislike. And also, as you said correctly, ambiguities in the environment is a critical point for that. So we'll look into those two things, and I would start with that with just showing you 3 different examples of systems that we have built here in Freiburg. No, that's not true. The first one and the last one are Freiburg vehicles. This is not a Freiburg vehicle, but some of the mapping techniques we developed here have been used or at least tested on that car. So this is a Pioneer A2 robot, which has a 2D laser rangefinder sitting here, and it sits on a pan tilt unit. So it moves always like this, so it's called a nodding laser. And this way it generates 3D data. You get 3D information about the scene. And then it tries to build a 3D map of the environment using this technique. Okay, so let's start with this one. The robot provides odometry, and the laser range scanner, a 2D laser range scanner, sits on a pin tilt unit. We may assume the robot is standing still when doing its scans. Maybe it's driving while it's taking its scans. Driving may make it a little bit more complicated if you have not a good odometry estimate, because while driving you don't observe the same part of the environment, and this makes it hard to make any incremental alignment. And the maps we may get out of that look like this. So what you can see here, red means non-drivable areas, yellow means drivable area. So this is building 79. This is the street. Here it goes down to the parking lot. So this is an example of a map that you might obtain with this approach. How does it work? Okay, we have the robot. It uses odometry information. So it moves forward, takes a 3D scan. And what we can then do, based on the odometry information and based on our local 3D scans, we can actually build a map. We can build a local 3D map of the scene. this map can be either a point cloud accumulated over multiple poses, multiple scans. It may also be represented by a 3D grid structure or by a more efficient data structure, such as an octree or multi-level surface maps or other map representations that you may have seen in Introduction to Mobile Robotics, or that you will hear next term in Introduction to Mobile Robotics, hopefully. How the local environment representation exactly looks like doesn't really matter at that point, but that's one way that we build kind of a rigid structure which contains the 3D information. That's kind of the important part in here. And then the robot continues, odometry information, drives 5 meters forward, takes another range scan, and builds another local map. And then what we can do is we can take those 2 local maps and try to align those 2 local maps. It's typically in advance, so depending on how many scans you integrate, either you could take these scans, so if it's just kind of one 3D scan, you would, although in practice these are a number of 2D scans, for matching it's much easier to have one 3D scan. You can either take one single 3D scan, you may even combine multiple 3D scans if you have a good pose estimate between those individual scans. And sometimes it's easier to match full maps versus individual scans. This depends on the data that you have and how many ambiguities you may find in your environment. So if you have a slightly bigger view, so you really match a map against a map, that may be easier or may have less local minima. So we match those maps and get a 6 degree of freedom constraint, in this case x, y, z, yaw, pitch, and roll, so a 6-dimensional constraint. And then this is actually one of those constraints here. Then we can accumulate all constraints and then do a graph optimization and obtain a local map. So this is also a part. So this is building 79, building 51, 52, the Mensa building, and of course some parts here, the green area, which robot hasn't seen. How does it align those 2 scans? So these are 2 examples of 2 scans, of 2 of those 3D scans, and which have been taken from different positions. And this kind of an iterative alignment procedure, very similar to ICP, that aligns those scans. So what the approach here takes additionally into account, it kind of separates areas like such as just a simple, let's say, classification or segmentation of the environment, like identify walls, things that stick out, and first matches those against each other, and only in the end it does the alignment of all points because you're less likely to end up in a local minima. So if you, let's take the tree, the pole, and the walls and match them first, if you can separate those part of the scan reliably, you typically are less likely to end up in a local minima. And then in the end, you get this kind of alignment. So it's an iterative procedure based on ICP, which align those scans. And then I can do this for a large number of individual scans, and then I end up with a map like this. So you can see, you may observe some of those small stripes over here. So these kind of darker stripes. These are simply small alignment errors of these individual maps. They can see kind of small steps over here. Here there was also probably an alignment error, which simply leads to a step which was, let's say, bigger than, I don't know, 5 centimeters in the ground, and therefore it's classified as not traversable anymore, and therefore everything is red over here. But so what you see here, for example, are the bikes which are parked over here and the individual trees. Here something is likely to have gone wrong, or maybe there was some, no, that can't be. This was maybe a car coming here from the parking lot, but this area over here seems to be alignment errors or slightly misaligned scans. But that's the way you can actually use 3D data to build a map of the environment. Next example. This is an autonomous car. It has a 3D scanner here on top. So that's a Velodyne 3D scanner, which is rotating and generates 3D point clouds at a very high frequency. And you can use a very similar technique, or basically exactly the same technique, in order to align different poses of the vehicle. Here, you typically use an initial measurement unit to estimate the relative movement of the vehicle, because the car is of course driving while the scan is taken, so that you kind of really get more or less accurate endpoints of every single laser beam, even while the vehicle is driving. And you can again put that into a local map and apply exactly the same strategy as before If your initial estimate is better, if your laser data is a high quality laser data, then you get an example like this. You have seen this picture already. This is a parking lot or a 3D model of a parking lot where yellow again means drivable areas and red means non-drivable areas. And then you can actually use this, this map over here in order to localize the vehicle, in order to autonomous driving. That was actually a work of Rainer that he built, or he realized autonomous parking using this map representation, which was built here for that vehicle in that parking lot. So that's actually the picture of the parking garage. And so you can see even with here a 3-floor building and the corresponding 3D model where the car entered here. There's a trajectory of the car doing the mapping process. So started from here, stopped from here, and built a map. And so these were kind of, in this case, 1,600 local 3D maps. And this was in this example done with the grid of 20 by 20 centimeter grid cells. And this, by aligning those grid cells, you can actually get maps of, let's say, this quality. That's something you can expect to get with this technique. Okay, how does it look like if we look into cameras and maybe flying vehicles? If you go to flying vehicles, you typically have the problem that you have weight limitations. So whatever those vehicles need to lift should be as lightweight as possible. And the more lightweight sensors are, typically the more crappier the quality of those sensors is. So in this case was a system which was flying on a prototype for a helicopter, so it never made it to the Blimp in the end. This was just a self-assembled stereo camera system with 2 webcams assembled in a stereo setup and a small IMU. This is an inertial measurement unit. And one of the advantages of this system is it gives you also the gravity vector. This quite accurately at a high frequency. And if you know the gravity vector, you can eliminate already 2 of the 6 dimensions from your state space because the roll angle and the pitch angle can be determined just by knowing the gravity. So you have only one angular component and x, y, z that you need to estimate. And therefore, adding this IMU to the to a stereo system is highly advantageous because it removes 2 degrees of freedom. They estimate quite accurately. You could even use this to estimate the movement of the camera or get an estimate of the movement of the camera, but this was not used actually here in this example at least. So these are the camera images you typically get. So it's kind of a webcam of 2008, I would say. So 2007, yeah. These times this was actually the work of Bastian Steder, his master thesis when he did that. And these are the piles you can see. These are the piles in our building. These are the piles in front of our building and the grass area. So if you take the stereo camera, point it downwards, and walk over the green, these are images that you get. And if you see this image, you may already guess that it's maybe hard if you travel over grass for extended periods of time. But nevertheless, the approach works surprisingly robust and is able to estimate trajectory as well. So how does it do that? The first thing it does, it extracts features from the camera images. In this case, these are surf features. What these surf features actually provide is a local description of the scene, or of the small part of the image. And so you see for every of those points here, one of those descriptor values is computed, and they're computed kind of from a local window around them, doing some local operations and returning typically a 128-dimensional vector, which is a local description of the area over there. In reality, typically it's a 2-step process. First, a so-called key point detector is executed, which tries to find kind of, let's say, call it stable areas in the image. So if you have 2 similar images of the same scene and you want to compute those descriptor values at the same positions, and therefore you first run a key point detector. They typically look to the whatever corners in the image or edges and compute those features at corners or at blobs. So there are different ways on how this can be done. And then for every of those detected points, one of those feature descriptors is computed. And what the approach then does, it says, okay, based on for those points, I try to estimate where they are in the 3D space, just taking the stereo information into account, and based on the position of my stereo camera, I try to build a local model of the surrounding. So what we want to estimate is the x, y, z, and 3 angles, roll, pitch, and yaw. So if you have this your camera looking forward, this is roll, this is pitch, and this is yaw. And so as I said before, by adding this IMU to the stereo camera, and in this case the camera is looking downwards, and we have the IMU on top, we know the gravity vector. And so this eliminates the roll direction because this will change the gravity vector, and the pitch direction because it will change the gravity vector. So by knowing the gravity vector, I kind of get rid of the roll and the pitch. And this reduces my problem from 6 dimensions to 4 dimensions for every node or for every camera pose, which makes my life easier. And therefore, it is kind of exploited here. So based on that, I can, by a triangulation, compute where are the points in the 3D space, given that I see the points in both camera images. I only need to know 2 features, 2 of those descriptors, with their corresponding 3D coordinates in the image in order to estimate the relative pose of the camera. So in practice, it looks like this. So this was the camera pointing downwards. Let's say these are images which, and the red dots are positions for which those features have been computed. These are my features in the map. Let's say this is the current image that I observe. So I'm saying, okay, this looks like this. We'll transform it over here, and then you can take this image and add it to your map, or add a constraint between the position where this camera image has been taken, the current camera image has been taken, and the images have been taken at previous points in time. So in practice, these approaches, in order to be efficient, for example, what they do is you first try to find, so what you have your image, you extracted your surf features from your image, and you have a database of all the surf features that you have seen so far in the past. The first thing you do is you try to make a nearest neighbor query in the descriptor space to try to find the best matching descriptors over your whole map, or in those areas which are in line with the criterion in the beginning with these A's and B's which overlap. So either it's a full database or only those nodes where there's an overlap. And this, you can typically do that very efficiently with a KD tree. It's a data structure which allows you to search in log n time with a number of data points if you have a constant dimensionality. So that's a very efficient technique to do that. So based on this KD tree, you can, let's say I get the best 100 features which match the current feature I'm considering. I can do that for multiple features in my current image. This gives me already a pretty good idea where I might be. Okay, we said, okay, we need 2 matches in order to compute the transformation between the camera poses. So we have one set of features recorded at point T1 and one set of features computed at point T2. So we need to have the 3D coordinates of 2 features in each image, so 2 corresponding pairs in order to estimate where the cameras are, under the assumption that I have the IMU so that the roll and the pitch angle is given. So what we do is we take those matches and we simply sort those matches according to their quality. Simply start from the top. So we start with the best matches. We say, okay, let's take the first pair and with the first other matching pair in the other image, and let's compute where the camera poses should be given under the assumption that this pair is correct. And then we take all other features that we have seen, project them from one image and project them to the other image and see if the reprojection of the features actually match where we see the features. So we take a pair of feature out, compute the transformation based on them, and then take all others in order to evaluate how good this proposed transformation was. So I simply can repeat this process until I'm, let's say, happy or a good pose has been found. And this is a procedure that is very, very similar to RANSEC. It's actually a variant of GoodSec, I think, which was used here. But this is just, you sample a few parameters that you need in order to compute the solution, and then use all other informations to evaluate this solution. And then you try that multiple times and see how often do we find a consistent match. And that's the way this works. This technique is used in 3 different ways in this approach. The first one is for visual odometry. So there is no wheel encoder on the camera. So if you take the camera on a flying vehicle or we take it into our hand and moving it over the ground, there is no odometry in the classical sense. So there's no wheel encoder which counts the revolution of the wheels, and this way gives me an estimate of where the relative poses are. So what you can do is you can do what's called a visual odometry. So you inspect the images in consecutive frames, estimate the positions of features, and then estimate the movement of the camera based on the feature that you see and the 3D location of the features, exactly in the same way. So this is how we can actually generate odometry information, although we don't have a physical odometry information from wheel encoders. The second technique how you can use this is actually for matching your current observations against a small part of the environment. So under the assumption that I know where I am in my map, and I have a map, I can actually match my observations against the map. So it's kind of a localization step. So if the robot is retraversing an existing part of the environment, has a good estimate where it is, that is what we refer to as localization. And the last part, which is loop closing. So given I don't know where I am, so I have a large uncertainty, and you can use this approach to see how well do the features that I see at the moment match with features I've seen in the past, and try to find an alignment for this. And if this is a good alignment, you may accept that. Or you may try this for a couple of consecutive frames, that not just kind of one bad image screws up everything. So you may accumulate or wait until you find a few consistent constraints in order to integrate a match. That's what's done typically in reality. This is an example how this looks like. So this was Basti Steder in 2007. This is the stereo camera kind of on a fishing rod, so that it's kind of simulating a flying platform, which we didn't have at that time. And this is the current camera image that you see, the features that were extracted. And what you see here is a map that the system builds on the fly. And that's how that looks like. So walking over the green in the back of our building. So today this is all bushes and trees over there, so it's quite a while ago. You can still hear that the visual odometry, although the individual images look actually rather crappy, you're able to get at least an incrementally not too bad estimate of your trajectory, although it's globally pretty wrong, which you will see in the near future. So here the estimation works a little bit better on the tiles because you get better features to match. So in a few seconds, he will return to a place where he has been before. So here you can see actually he approaches is actually in reality here. So there's a substantial mismatch, but there are no features that are matched at the moment. And as soon as he goes back to its starting location, you will see that it finds some of the features which are consistent. You will see that some constraints will be added to that graph. So this is a place where you started. There was kind of a book of reference. You can see here it found some images and even found constraints along the grass because you know where he was walking and tries to walk along the same area again. This adds you all these kind of loop closing constraints or these constraints. These are now constraints where the system relocalizes the blue one because it's moving back on the trajectory. So you can apply the optimization. So these are the individual steps of the optimization and get out this trajectory with the corresponding images and feature locations that the system has observed. You can then even overlay that with our building. That was actually a Google Maps image of 2007, so the quality was bad. Today the quality is much better. You see it doesn't fit perfectly, so here I think he walked in between here, but the rough estimate of this trajectory actually is similar to where he was actually walking. You can actually evaluate that even better, so the same experiment you can do indoor, where you put in known markers in the scene or markers at known positions. Again, these boxes, we can see here then the stereo estimate. So this is just kind of taking the 3D positions of those features and doing kind of a mapping the textured image on those 3D points. This was kind of, I think, whatever, 1.5 by 5 or by 10 meter, where different markers were placed on the ground, which were measured. This was measurement tape, so not the absolutely perfect, high accurate measurement, but let's say up to a centimeter or something like this. And then you can actually revisit the same place, and this way close the loop, and then estimate where are the marker positions in between the map and reality. So you can see here all the constraints that the system found, does the graph optimization, and turns it into an estimate of the environment. And this is the resulting map you can see. So this is the trajectory that the camera took And here, this is just kind of the this was one of those boxes, was just taking the camera images and projecting it to the, or mapping it to the 3D point structure. Because we have the 3D pose information only for those feature points, so we don't have that for the overall image. You can actually overlay that, so it's exactly 1.5 by 10 meters, and you can actually see that the estimate. So this is the ground truth information, the green lines, and this is the mean and uncertainty that was estimated. So at least it seems to be a somewhat consistent estimate. You may see a small bias. It's not centered around 0, but given kind of the self-made stereo setup just with gluing 2 cameras together, that was actually a really nice result. Then you can use the same system, for example, on a blimp. This was an example where we used it. In the end, what we used here was exactly the same approach, but only a single camera and a sonar, which was measuring the depth information. And so this was a blimp, and the task of the blimp was always to hover on top of this location, which was here marked by the book. That's, I think, somewhere over here or here. And so it's always trying to hover, and whenever it hovered, this is the hovering location, someone took it and threw it away. So the robot was going somewhere else, building a map of the scene, trying to find again a place which I've seen before, to relocalize. Whenever it relocalized, try to estimate where it should go in order to build a map, in order to find back its home location, and in order to hover over this place. And also you see here, whenever someone opens the door, there's a lot of wind going in there, so it's actually a little bit tricky for the platform to always hover, or people walking by. And yeah. Okay, and then someone again pushing the platform away. Okay. So this was actually, this is an example where one of these platforms uses the map in order to solve the navigation task. So it builds a map online and uses the map in order to make navigation decisions of where it should actually go. And so it's an online process which requires us to build the map, to update the map, and always come up with a consistent estimate of the map in order to generate steering commands which always guide the platform back to the desired location. In this case, again, it should hover here at one location. Okay. So these are 2 problems we discussed, or we said how can we solve that. So the ICP is sensitive to the initial guess. So one thing we can do is try to arrange things into maps instead of single scans. This helps. Or we can separate the local perceptions into some parts. Let's take these walls or these obstacles that stick out and try to match them first. We are less likely to end up in a local minimap, but of course there's no guarantee for doing that. And also the inefficient sampling strategy, if you have descriptors, like feature descriptors, it can actually help you to find good estimates where you can be. So you don't have to try all camera poses and see if the camera poses match. You can use your feature descriptors to already pre-select images you may consider for potential loop closures. So this was kind of the first part of the talk, which kind of was a more lightweight overview about how different approaches work with not going into too many details. In the second part of the talk today, I would like to talk about ambiguities in the environment and what are good ways for dealing with ambiguities, and how can we actually, even though we have environments with ambiguities, build accurate maps, consistent maps of the environment. So the main assumption here is not we simply ignore all ambiguities and say the environment has no ambiguities, and I just consider there are none of them. If you say there may be ambiguities, and how can I actually deal with that? And this is one of the approaches which does that nicely. So we'll start with the motivating example. So again, we have our example with A and B. This is the place A, which is the current view of the robot, let's say a local view. And let's say I have a map and a place B. Say this actually place here looks pretty similar to this place over here. So are A and B the same place? In the ICP-based matching approach, we would say, okay, let's sample some positions here and then try if we can find a match. And actually, we will find a match here. So this will match this structure here quite well for an ICP-based alignment technique. But we could always argue, is this the same place? What's the problem? Can we make the statement, is this the same place or not in this example? Why not?
Well, it could be
Especially here is a white area, a lot of white area.
So it could be a repeating structure there.
Exactly. So the only thing we can say is that A and B might be the same place, but there might be something else which looks exactly like this place A here. So it may not be a good idea to add this constraint unless we have seen all this part over here. Actually, if you look into reality, that's how the structure looks like. And these are 3 matching hypotheses, and this one is the correct one. So in order to make this constraint, maybe it's better to first explore all this scene over here before we can make this data association. And this is something which is called global ambiguity or something. So there may be different places where the system can be which do not intersect with the place I'm currently considering, and therefore I should not do a match.
Yeah, but if you have to explore the whole area B before you can match A, if you want to explore it, you have to know where you are, so you have to match other things.
But you could, I mean, this was just an example on that you want to make sure. So there are 2 ways you can do that. The first thing is try to make sure to close your loops as early as possible, so don't let the uncertainty grow so much. And the area is smaller, it's more likely that you find a match. The other thing is you could simply cover the whole area so that the ellipse is 1 in there. And once you found one where it matches, then the uncertainty of all others will decrease, and this helps the system. So we are not doing here the active approach of on how to explore in order to build a good map. So this was just kind of a floppy statement that I made. Here we are really looking just into SLAM. So someone is steering the platform, and we just want to make the decisions. Is there a constraint or not? So it may be a bit imprecise from what I told before. So here's a global ambiguity, which is something we don't want to have. In the other example, if the uncertainty is small, and I have this match over here, you say, okay, that looks good. That's kind of what's called global sufficiency, so the opposite side. So this is a globally sufficient match. So there's no other place in the uncertainty area of that node where the system can, so there's no other place in here where A would fit in. And these are the things I'm interested in. Finding exactly those situations. I say, simply the match can't be anywhere else. However, there's a second problem of ambiguities, which is called a local ambiguity. Because if I introduce a global ambiguity, there's quite likely to be a local ambiguity. And this is, for example, this structure here. You have the corridor, and these are kind of the parts of the doors, or the whatever small pillar which holds the door, in Deutsch Türzage, which you can see here. And you actually see multiples of them in the map and in your scan, because it's a repetitive structure. So you say A is either here or here or here. So this is my uncertainty. Although there's no other place where A matches in this uncertainty ellipse, there are multiple hypotheses how it can match inside. And they overlap. Therefore, it's local. The other one was non-overlapping. It's global. And this is our overlapping matches is global. So I don't know how this A fits in here. So does this guy over here fits this one, or this one? So either here, here, or here. Simply something it's hard for me to identify. And this is also what's called the picket fence problem. So you have a fence, you simply don't know which part of the fence matches to what you see so far. It's a very, very long repetitive structure. And these are things where you also don't want to add a constraint because you simply do not know, is this locally ambiguous or not? If it is, you typically don't want to add a constraint. You can only say it's either here, here, or here. What you could do is you could use the max mixture approach and say, simply it's a multimodal constraint that I may add. I'm either here, here, or here. But at that time when this approach was proposed, there was no max mixture yet. And therefore, it's not foreseen, although it was actually the same author, Edwin Olson and his group, who developed this approach and later on max mixtures. So this would be one nice application for max mixtures. But assuming we don't have max mixtures, we have to treat those things separately. Okay, what can we do? We can actually do 2 tests. The first one is a global sufficiency test. So we want to say there is no possible disjoint match in the uncertainty ellipse. That means A cannot be completely somewhere else. There's no possibility that A can be somewhere at a completely different place. And the second thing, we want to have local unambiguity. So there are no overlapping matches. So there's A is either here or somewhere else entirely. So there's no, so I cannot, by just rearranging the scans a little bit, find another good match. These are two things I want to avoid, or I want to make sure that both constraints, both conditions actually hold. And the approach that Edwin Olson and his team proposed were saying, okay, we have our SLAM backend. It gives me an estimate, kind of the current estimate of the graph that I have. And I do it does a post-to-post scan matching, very similar to what you've seen so far. And based on the scan matching, we can actually do a topological grouping. So poses which are nearby, which are in the same part of the environment, are just grouped together. So you can see this is a small local map. There's actually nothing bad about that. Just poses which are nearby can be grouped together into kind of a local map, but very similar to the hierarchical post-graph approach with doing that. And then it does two things. The first thing is it tries to find within those groups of those topologically grouped nodes, it tries to find consistent constraints. So how many constraints I can find in there which are consistent among each other. If some say either I'm 1 meter to the left or I'm 2 meters to the left, this is an indicator for this picket fence problem. It can be, like in the corridor, it can be either here, 1 meter forward, or 2 meter forward, or 3 meter forward, but nothing in between. And so that means I find typically a lot of constraints in this local group, and I can find subsets of those constraints which agree with each other, and others which don't agree with each other, which don't agree with the other solutions. And the first step is trying to identify this situation, and the second thing is once I've eliminated that, I do kind of a global ambiguity test, which is much simpler, which basically takes into account what's the area that I know, given the uncertainty ellipse that I have, and is there another local area of what I've seen which would fit in there and still would allow for a match. And with getting rid of those two, doing these two tests, we can actually eliminate a very, very large number of false positive constraints. So that's actually one of the state-of-the-art systems which are used in SLAM front ends and also runs in, I would say, most or if not all of the mapping systems that we use here in Freiburg, runs this system in order to identify or in order to filter constraint that the system may have found based on the sensor observations and say this seems to be okay or this seems to be a wrong constraint. Okay, so this is the criterion one. The second criterion for the local ambiguity and global sufficiency. So, or local unambiguity and global sufficiency. Though these are these two tests I have. Okay, I would like to go through these 3 steps over here. The first one is the topological grouping, which is easily done. So I just take my post graph and I just say, okay, which poses are nearby, and then I try to match all of them. So this is kind of one local match group, and a second local match group, and I just see if I can match all of them in, for example, a pairwise fashion. Whenever my matcher says, yeah, it could be a good fit, maybe, yeah, doesn't sound too bad, just add them to kind of a temporary constraint list. And this is shown here in red. So this one can match against this pose, this pose, this pose, against this pose, this pose, this pose, and this guy here against these 2 poses. Some of them are likely to be right. Some of them are very likely to be wrong. And the question is, how do I identify which one are right and which one are wrong? Again, the first thing we do is we want to test for local unambiguity. So we take one of those groups and check, okay, is here the risk for a picket fence problem? How can we do that? Okay, so if I match all against all and add all, like in this shown existing example over here, so I match all against all, and those which are above a certain threshold I keep, the others I remove. If I would optimize this map, I would get this situation over here. You can see here there are kind of walls which are duplicated, so it's definitely an imprecise map of the environment. If I, however, find only those which are the right ones, which are these matchings over here, I actually get a consistent map of the environment. And because of this structure over here, you can see this structure and this structure, and here actually a structure which may be seen again as similar. You have this picket fence situation over here. And the question is, how do we go from here to here? That's the kind of the thing we want to answer now. It makes this decision, which are the local matches, and is there an ambiguity and local ambiguity or not? If not, I'm happy. If there's a local ambiguity, I may say, okay, it's better to not add a constraint. Okay, locally consistent matches. How do we actually get those locally consistent matches? That's one of the key questions here. The key trick in here is we have a large number of constraints, pairwise constraints between nodes, and we want to check into how many consistent subgroups are there. So if I can assign a kind of a group ID to every constraint, and the goal is that among one group, or within one group, they're all consistent with each other. That's would be the perfect thing. But maybe I find two groups where within the group they all agree with each other, but not between the groups. So between group 1 and group 2, we say there is a different transformation between the posts of the sensor, but within a group they all agree. And this is one of those situations where I can see, which is an indicator for this picket fence problem. Okay, how does it look like? Okay, given we have a few or two sequences of a trajectory, once where the robot first time visited the place, which is shown here in red, and the second time when the robot visited the place here shown in blue, and I get those matching constraints in this case. So HI and HJ is just two hypotheses for constraints, how that can look like. And the idea is to say, okay, in order to check which are consistent, I need to check if they kind of transform the environment in the same way. And it's done here by taking what's here called the prior edges. These are those edges which result from odometry or incremental scan matching. If I start from this node over here, I can take my let's say my odometry constraint to go here. I take my constraint Hj to jump into the second trajectory, so the point in time when I visited the place a second time, move along the odometry again, and then go back kind of with the inverted Hi and go back to the same place. So if I have this kind of loop of constraints, if they are all perfect and agree and consistent, I should add an identity transformation if I concatenate all of them, because I'm kind of starting at pose 1 in the first time series, go to pose 2 in the first time visit. Then I take the matching constraint and I walk to the time 1 at the second visit, go to time 2 at the second visit, and then go back to time 1 in the first visit. And only if those constraints agree with each other and together with the odometry information that was collected, I will end up at an identity transformation. And so the trick is now to use all those pairs of constraints and see which one end up with an identity, and what is the biggest group of consistent transformation that I can find in here. You look a bit skeptical.
Yeah, I don't really think you will ever end up with a real identity matrix.
Of course. You will end up with something which is close to an identity matrix. So I'm happy with, of course, I'm not enforcing an exact identity matrix, but something similar, and because the similarity or how far you're away from your identity matrix simply depends on how accurate is your odometry information and how accurate can you actually align your scans. So, of course, modulo that. Yeah. Okay, so I have whatever number of those hypotheses. What I can do is I can actually build up a matrix, Ij, where this simply depends how consistent are the hypotheses, using the hypothesis I and the hypothesis J together with the odometry. So this is Ij, so I just kind of make this walk around in my graph and say, how close am I with respect to the identity? If I'm close to identity, I say, hey, that's pretty good. If I'm far away from identity, I say, something has gone wrong here. And this is a value which I get in here. So the probability that along this loop Ij, which takes hypothesis I and hypothesis J, we end up having an identity transformation given those two constraints. And these are values which are sitting here. So they are high values. If they say it's very likely I'm at the identity, that's a bad thing which can happen to me. Or I'm getting a really low score close to 0, which basically means I'm far away from identity. So you may use just a Gaussian about how far you're away from the identity. So what you end up, you have a matrix with those values in here, and some values have we have some elements with high values in here and some elements with small values in here. And this is just the matrix which tells me how well do individual hypotheses agree with each other pairwise. Okay? So it's clear to everyone what this matrix means, because we will need it later on, and if you don't understand what the matrix means, it will be hard. So every entry of this matrix, ij, tells how well do hypothesis I and hypothesis j agree with each other, just looking to this pair of hypotheses, just a pairwise consistency match. If there are small values in there, maybe they don't agree. If there are high values in there, they agree. That may be good. Again, this so far hasn't helped me to identify these groups, or if they are different groups. Just says which pairs are consistent with each other. Okay, what I now can do is I can define an indicator vector, which just consists of 0 and 1s. And the indicator vector is one hypothesis for consistent constraints. So if I have this indicator vector here, every element here, so it consists of 0 and 1s, and if I have a 1 here at the field I, it means that the assumption that hi is correct. And if there's a 0, that if aj is incorrect, or it's not correct. So I get every vector consists of 0 and 1s, and is one hypothesis about the consistency of my matches. If I have in there 1, 1, 1, 1, 1, 1, 1, 1, 1, means it's pretty good. It means all of them agree with all of them are correct. If all of them are 0, which means it's completely incorrect. It's just, so the goal is just to define this vector and then later on find a way and how can we determine what this vector v, or indicator vector v should look like. But so far, the indicator vector just says, if there's a 1 in there, it's correct. If there's a 0 in there, it's incorrect. And now comes the trick. We combine this indicator vector with my matrix. So I multiply this vector with my matrix. If I multiply this vector v with my matrix A, it says for an hypothesis that hi is correct and maybe hj is correct, so if, let's say, I and j are 1, the rest is 0, it will directly take out the corresponding value of my matrix A for the consistency of I and j. So if I do this operation, I say my indicator vector v transpose times my matrix A times my vector v. This gives me the sums of all consistent hypotheses according to the indicator vector. If all of them are 1, I have the sum of the elements of the matrix. If only 2 elements are 1 and all of 0, just get the corresponding element out. And then I divide it simply by v transpose times v, so the scalar product of this vector v, which is simply the number of hypotheses which are correct according to this vector. So just an average. Because it consists of 0 and 1s, they are the same vector, so whenever both elements are 1, I just add plus 1. So what I get in here is, this is the sum of all consistencies between pairwise hypotheses in this indicator vector divided by the number of hypotheses. So it's kind of the average pairwise consistency. So now given an indicator vector v, I can compute this quantity here, and this gives me a score. And the higher the score, the better. So if I have a group where everything agrees, I can add all the 1s, 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 1s in this vector, and I will get a high score. If I have ever 2 groups in there, I get scores among the groups, but not between each other. So we'll get and I divide by, again, a large number of hypotheses, so we'll get a small value. So I have this function, which has high values for good elements and low values for bad hypotheses. So what can I do? again, treat it as an optimization problem. I try to find the vector v which maximizes this function. That's exactly what is done. It's like, hey, my lambda is now function. Lambda is depends on my variable indicator vector v, and I try to maximize this expression. The problem I have in here is that my indicator vector v has a constraint that it only allowed to take zeros and ones. And under this constraint, there is an NP-hard problem. There's a corresponding densest subgraph problem, which is an NP-hard problem. So in order to find the best v, I actually need to try out all possible solutions, which is something which, for a large number of constraints, simply doesn't work out. Therefore, the idea is, okay, I know how to compute it, but it's too computationally demanding to do that. Let's see if we try and find an approximation out of that. And we actually find a pretty good approximation for that by saying, okay, I simply don't treat my vector v as discrete. I just allow continuous variables, because then I can actually optimize this, and then get a solution. In the end, I simply round to 0 or 1. It may not be perfect, but it's actually under the assumption that the continuous problem reveals a similar structure than the discrete problem, I should come up with a very similar solution. There's no guarantee that this is the case. So it is definitely an approximation. It's a different problem that I solve if I go from discrete value, from discrete or from 0 and 1s, from binary variables to continuous variables. But the assumption is that I'm not too far away. But there's no theoretical guarantee for that. Okay, how do I maximize this function? I compute the first derivative. I set the first derivative to 0. I don't want to go into the details how the derivative is obtained, but it turns out solving this equation is equivalent to solving this equation over here. If you may look to this equation over here for symmetric matrices A, so does this formula look familiar to you?
It's the eigenvalue.
Exactly, it's the eigenvalue problem. So matrix A vector V is equal to a scalar times V. So in order to solve this problem, I simply need to solve an eigenvector eigenvalue problem. So I need to actually solve this problem over here of finding the eigenvector and the eigenvalues. And I can just solve that in whatever solving technique I want to use. For determine this, I could use the SVD that we discussed, for example, with the diagonalization in whatever, a few months ago when we discussed this. I don't know in which context we did that, but we did that in the course. Or you can solve the characteristic polynomial in order to do that. And what you do is you get a set of eigenvalues and a set of eigenvectors. And what we then do is we look into the and so the vectors v that maximizes this equation, the original equation, is kind of the maximum consistent subset, or the average maximum consistent subset. And if I have multiple solutions for that, get multiple. So if I have multiple solutions for this eigenvalue problem, this is simply there are multiple maxima in my problem. I can actually inspect the individual eigenvalues and eigenvectors and check how large the eigenvalues are. And so the larger the eigenvalues are, the better the score. So there's I get a perfect combination. I get a couple of eigenvectors with corresponding eigenvalues. The larger the eigenvalue, the higher the score, and the eigenvector allows me to say, okay, which of the constraints should I switch on and off? So if I visualize this, so I have one situation over here. So this is kind of the first eigenvector, second eigenvector, third, fourth, and this is lambda I. If this is kind of a high value, this is a low value, low value, low value. Make it even low value like this. Would say there's the first solution, which corresponds to lambda 1 v1, so the indicator of v1, which gives me the score lambda 1, which is the highest score I get. This is kind of the best solution that I have. And all other solutions are much worse in performance. If I say, however, okay, I have this example over here. That means solution 1, 2, and 3 perform more or less the same, get more or less the same score. So in this case, lambda 2 equals, or approximatively, lambda 3, which is approximatively lambda 1. And I have different indicator vectors. That means I have 3 different solutions which give me more or less the same consistency score. That could, and this is exactly the identicator for one of this picket fence problem. I have different consistent subset of constraints but they don't agree with each other. So the only thing I need to do, if I want to say, is it a picket fence? Is a picket fence here? So do I have more than one solution? I can just say, okay, what's the ratio between the largest eigenvalue and the second largest eigenvalue? And if this is a value which is, let's say, 1 or between 1 and 2, I say, nah, this is very likely to be a picket fence problem because I have 2 solutions which are similar. If this is a value which is very large, so much larger than 1 or 2 or 3 or whatever I choose as my parameter in there, it means it's very, very unlikely that it's because the second solution is much worse than the first solution. Still, this assumes that let's say my topological grouping is done in a fair manner, and it includes all the relevant constraints. But under this assumption, that's exactly what I get out here. So what I do is I compute the first eigenvalue and the second eigenvalue, and I compare them. And let's say if lambda 1 divided by lambda 2 is larger than 2, then I say, okay, then I regard the solution 1 as locally unambiguous. That means there is no picket fence problem, with a high probability, of course. Still, maybe the case, I may make a decision, but that's my assumption here. What I then need to do, I need to discretize V1 to 0 and 1s in order to find my activation. There's one point in here, typically the eigenvector is normalized between 0 and 1. So this, if I would just round the vector V1, I would end up with probably having zeros everywhere. But that is easily solved because I just multiply this by a scalar, which is a kind of a 1D, so a kind of a constant times V1. The question is, I just need to find the constant which maximizes this function over here. So it's just a kind of 1D search problem in order to do the discretization. Because if I compute the eigenvalue problem, the eigenvectors are normalized. And I don't need it normalized. I really want to do the discretization. So what I do is I say, okay, I just know I'm somewhere along one vector as lies my solution. I just can have a 1D search problem in order to find the solution for this one. Because I know what V is. It's just kind of V times a constant C, and just need to determine this constant so that this expression is maximized. But V is already given, so that can be easily done. Okay, so now I solved the local ambiguity problem. Or at least I'm able, in a situation where I can say, there is a picket fence problem here or not. So that's actually the first thing I wanted to check. Is there a picket fence, yes or no? And that's actually a very, very nice way for identifying that. The second thing is quite easy. Not quite easy. The second question is, so if this is one potential match, is there some area around this area A within this ellipse so that A would fit a second time in there? So something I haven't seen, for example. Or is there enough wide area so that A would fit in there a second time? If this is the case, I may say, I can't be sure that this is a constraint. It could be a constraint, but I'm not sure that it really is a constraint because there's simply an area in the uncertainty, in the relevant uncertainty area, which I haven't seen so far. And what we would, in theory, need to do, we need to really check this area, can see if we can fit it in here. An approximation for that is I just compute the the size of the ellipse, this circle, and the ellipse over here. I compute again the eigenvalues of those two, which tells me, so if the eigenvalues are the same for x and y, it means it's a circle, and the larger is in one dimension, the larger the main axis is. And I just can compare if the smallest eigenvalue in here is larger than the largest eigenvalue of this guy minus the one of this guy. There may be a possibility to squeeze it in there. just by comparing the eigenvalues along the dominant axis of those ellipses, I can actually do that. Again, if I have very, very narrow matches, this may have very, very narrow corridors, this approximation may lead to a failure because I may be able to squeeze it somewhere in there, but that's not the case for most examples. So in this sense, I kind of completed the pipeline. So this was kind of the thing we spent most time on, and try to solve this criterion 2 for the test of local unambiguity. And if I find a picket fence problem, I simply say I just abort it and say don't add a constraint. If it passes the tests, I do the global ambiguity test or global sufficiency test. So is it globally sufficient, or is there a global ambiguity? If there's an ambiguity, don't add anything, and otherwise I have a loop closure which I can say with a high likelihood it's globally consistent and there's no local ambiguity. And that's a way actually most or a lot of different SLAM system works. Also the SLAM system that we use in here, and you have seen this video already, where the system, we have the robot mapping our campus over here. So we start in front of our building, continue moving, and this one exactly does this. So you can see if the area turns red, this is actually the place where it looks for potential loop closures based on the uncertainty, and then it tries to find them and collects a few of them, groups them, sees if there is a picket fence problem, sees if there is a local an ambiguous situation on a global scale, and if not, it adds the constraints, and in this way builds a map of the environment. And this is kind of basically the front end here is an re-implementation or an implementation of the method of Edwin Olson in order to make this test over here. And we found that as very successful techniques in order to solve the SLAM problem and not add false positives constraints, or add only very, very small number of false positive constraints. Okay, so to conclude this talk today, I know that was kind of compared the front ends to the back ends. This was kind of much more back ends in this lecture than front ends, but at least I tried to give you an idea on how front end works. In the end, it strongly depends on the sensors that I'm using, and I need to, the better I can exploit the individual properties of my sensor, the better it is. And so how this is done exactly strongly depends on the sensor. It's hard to give kind of a general framework for that. But the approach of this global ambiguity test and the local ambiguity test, these are important things that a good front end should consider in order to avoid adding false positives constraints. And this is done with this single graph partitioning approach. This was kind of the techniques, the technique of Edwin Olson, which uses this. Yeah, again, so regarding the positional uncertainty of the platform, the higher the uncertainty is in an area, the better I need to know the area in order to make the decision. Is there a global ambiguity or not? It's kind of, if the uncertainty ellipse is big, I need to see in all that area in order to make the decision. No, that's the only place where I actually can match. And about the spectral clustering technique, so the original paper where you find all the information here is the work by Edwin Olson, recognizing places using spectral clustered local matches. This is exactly the approach that I presented here. And actually, a couple of the slides that I used in here, or of the images material at least, comes from Edwin Olson. And thanks, Edwin, for allowing me to use that. And that's it from my side for the front ends. And the only thing I would like to do after this lecture is give a very 10-minute summary about the most important things of the lecture that you